Hello and welcome to this video. In this video, so we are still in section 2.1, we are going to talk about Goursat-Cauchy theorem and two of its consequences. But before we state the theorem, actually, we just have to be precise about the language. So we will distinguish between a triangle and a triangular region, okay? So for us, a triangle is just the three sides. So it's the boundary, actually. So a triangle is just the boundary, and the triangle region is the boundary and what is inside. You can call it solid triangle, okay? So for us, a triangle region is the area bounded by a triangle, okay? And we can define, we can define a triangle region actually how? By the set of points joining a vertex to points in the opposite sides. Okay, I will do a picture later. Okay, so if gamma is a triangle loop or just a triangle if you like, but when we say loop it means it's oriented. If gamma, if we have a triangle loop inside an open set omega, if omega contains holes, the interior of the loop need not be in the loop. It need not be in the omega. Okay, for example, if you take the domain in green here, omega, so there is a hole. If I have a triangle surrounding the hole, then the interior of the triangle or the triangle region is not contained in omega. Okay, so it's important to be precise about these concepts. Okay, however, so we shall get back later to the problem of domains containing holes. Okay, but note that if omega is convex, right, and if I have a triangular loop gamma, then the triangular region bounded by this loop is totally contained in the domain. Why? Because, okay, take a vertex of the triangular loop and join it to a point in the opposite side. Okay, if the triangular loop is contained in the domain and the domain is convex, so we have 2 points in the domain, one vertex and the point on the opposite side. So convexity tells me that the whole straight line segment joining these 2 points is totally in omega in the domain, which is convex. And if I repeat that to other points, I cover the whole triangular region. So the interior of a triangular loop in the convex domain is contained in the domain. Okay. So, and now having precised all these facts, we can state the main theorem of this video, but I need a very simple algebraic lemma first that I will use. If you have 4 complex numbers, Z1, Z2, Z3, Z4, and consider their sum Z, then I claim that 1/4 of the modulus of the sum is less or equal than the modulus of one of them. So if you like, one of them of these 4 numbers in modulus is at least as great as 1/4 of the modulus of the total sum. Okay? Or if you like, modulus of Z less than 4 modulus of ZK. Same thing. This is very easy because we reason by contradiction. If this is not true, then we have 1/4 modulus of the sum is bigger than all ZK in modulus. And if we sum them, so 1/4 modulus of Z 4 times, and I do the summation here, I get modulus of Z is bigger than the sum of the moduli. But the sum of the moduli by the triangle inequality is bigger than the modulus of the sum. So modulus of the sum less or equal than the sum of the moduli. So we get a contradiction. Okay? Okay, now we can state the main theorem of this video. Goursat-Cauchy, version 1. There is a second version also that we'll talk about in the next video. What does it say? If f is a holomorphic function, of course, on an open set, and T is a triangular region in omega, okay, so we are being precise here, okay, the solid triangle is in omega, then the integral of f along the boundary of this triangular region is 0, okay. Of course, here orientation is not really doesn't matter, because if you take the opposite so if it's the result is true for one orientation, it's true for the opposite because both are 0. Okay, but to fix the idea, we'll orient triangles in the counterclockwise sense. Okay, so call I the integral of f. We want to show that I is 0. Okay, now divide the triangular region T into 4 equal triangular regions, T1, T2, T3, T4. Okay, so this here's the figure. So start with a triangular region in green here, T, whose boundary is oriented. Orientation we'll see doesn't matter, but to fix the idea, orient it in the usual way, trigonometric way, and take the midpoints of the sides, okay, and form the first triangle, T1, the second triangle in the middle, joining the middle points of the sides. This is T2, oriented in the same by conserving the orientation. Okay, so you have to be consistent in the orientation. T3 as okay, and T4. Okay. So what do we observe here? Actually, the sides joining the middle points are actually when we integrate, so they are traversed in opposite directions actually. Okay, so when I write the integral over the boundary of T1 plus the integral of the boundary of T2 plus the integral over the boundary of T3 plus the bound, what do we see? The integral actually cancel here. So we get what? We get something very interesting. The integral along the boundary of the triangle is equal to the sum of the integrals along the boundaries of each of these triangular regions. Okay? So that's it. Now, if we apply the lemma, we have a complex number equal to 4 other complex numbers. So one of them, at least, is bigger than 1/4 of the modulus of the sum. Okay? And call this triangle region T1, T sub 1, in order to distinguish it between, because T sub 1 could be T1 or T2 or T3 or T4. Okay? Actually, it's not really important. Okay? So we have that the integral, I'll draw a picture now, over the boundary of one small triangle is bigger than 1/4 of the integral over the whole triangle. Okay. And now we repeat the process. So suppose that T1 is here, is this one. Okay. We cut the triangle also in half, and you have 4 similar triangles. One of them in modulus is bigger than 1/4 of the integral over this T1. Okay. So what happens actually if we repeat this procedure at each step? Okay, if we go back here, if this is T1, so T was the green region. T1 is this. Okay, so the sides are cut in half. So the diameter is divided by 2 at each step. And so the area is divided by what? By 4. Okay, and the diameter, which is the length of the biggest side, is also divided by 2. So perimeter is divided by 2. Diameter is divided by 2 at each step. Okay, we'll use this remark later. So repeat the construction. Okay, we get a second triangle T2 here, for example. Okay, at the second step. So the integral over the boundary of this triangle T2 will be bigger than what? Than 1/4 times 1/4 of the modulus of I, right? And we repeat this procedure again and again. So we construct a decreasing sequence of triangular regions, okay, nested sequence if you like, such that the integral over at the n step is bigger than 1 over 4 to the n times the modulus of I, which we want to show that is 0. So call In this integral over the small triangle Tn. Now, as you observed, the diameter of the nth triangle, the process, is the diameter of the original triangle divided by 2 to the n, because at each step divided by 2. So the diameter of Tn tends to 0 as n tends to infinity. And this was clear from the picture. And now we have a theorem in topology that states that, so in a general form, in a complete metric space, if we have a decreasing sequence of closed sets whose diameter tends to 0, then the whole intersection is just actually a one-point set. And this should be intuitively clear. Okay. So call A the point of intersection of all these triangles. So it's what we are left at the end of the process. Okay, you are left with just one point. And now, since f is holomorphic at A, we can write f of z in the usual way as f of A plus z minus A f prime of A. This is the linear part, plus z minus A times a quantity tending to 0. Okay, so this is just another way of writing the condition of holomorphy at A, at the point A. Okay. So if you like, you can write f of z minus f of A over z minus A minus f prime of A tends to 0. Same thing. So epsilon of z is what? Is actually f of z minus f of A over z minus A minus f prime of A. Okay, and now we integrate that. So the integral over the boundary of the nth triangle. So we get the integral over the linear part plus the integral of this mysterious quantity that we don't know exactly what it is. Okay, it's a ratio here, but cannot compute it explicitly. Now, if you look at the first integral here, this is just a first order polynomial in z, right? So it has an antiderivative. So an antiderivative of f of A is just f of Az, and an antiderivative of this first order monomial is f prime of A over 2 times z minus A squared. So by Barrow's rule, the integral over this integral actually is 0 because it's an integral over a loop of a function having an antiderivative. So this term cancels. So we are left with this term, and we'll prove that it tends to 0 actually faster than 4n. Okay. So just equate, take the modulus now, and we can apply the basic estimate of the modulus of an integral. It's less than the length of the loop, okay, times the supremum of the modulus of the function inside. And if we take the modulus of this function inside, actually, we get it's less than the supremum of modulus of z minus A times the supremum of epsilon z, of course, over the boundary of the nth triangle, which is very small. Now, z and A are both in Tn. Now, need not be in the boundary. Z is in the boundary, but A is not in the boundary, actually. But it's not a big deal, because the supremum over the boundary is less than the supremum over Tn, okay, which is the diameter of Tn. And the diameter of Tn, as you observe, is the diameter of T over 2 to the n, right? And the perimeter, this is just the perimeter of the loop, the triangle loop, it's divided by 2 at each step. So we get the boundary of the original triangle, the length, the perimeter, if you like, over 2n, times the diameter over 2n, times the supremum of this quantity that tends to 0 over Tn. Now, we are almost done, because this guy, In, is bigger than 1 over 4n times modulus of I. Okay? So after cancellation, so we get this inequality. And when we simplify by 4n, we get that the modulus of my integral is less than the perimeter times the diameter of the triangle times the supremum of epsilon of z over this small triangle Tn. Now, since by definition epsilon of z tends to 0 as z tends to a, and the diameter of Tn tends to 0, you can easily prove actually that this quantity tends to 0 also. Okay? If you don't believe me, go back to the definition and prove it. It's not difficult actually. Okay, so our assumptions imply that this quantity tends to 0. And these are constant, this is a constant. So when I let n tend to infinity, I get modulus of I is 0. So I is 0. So this concludes the proof of Goursat-Cauchy first form or version 1. Okay. Before we go to form 2 or version 2, we just have to draw two conclusions of this theorem. We have a first positive answer to the problem of existence of antiderivatives, because we saw earlier that not all functions possess an antiderivative. And we said that we need two things. We need a condition on the function and the condition on the domain. Now we have these things. So if omega is convex and f is holomorphic, then f has an antiderivative on omega. Okay, so this is a first big answer to our problem, the problem of existence of antiderivatives. Okay, why this is true? Because so we apply theorem 2.2, which tells me that when omega is convex, there is an equivalence between the existence of an antiderivative of f and the fact that the integral over any triangular loop is 0. Okay, but since we have now two things, we have to be precise here, because we have the concept of triangle loop and the concept of triangle region. Okay, so if you take a triangle loop in omega, since omega is convex, as you observed earlier, then the triangle loop is actually the boundary of a triangle region totally contained in omega. So because there's no hole. This is the intuitive reason, if you like. Okay, but we prove that why. So actually, we do an abuse of notation here, because we write gamma instead of gamma star, actually, because this is just really a curve, not a loop. Okay, but it's not a big deal if we use the right orientation. Okay. So anyway, if f is holomorphic, the integral over the boundary of a triangle loop by the previous theorem is 0. So therefore, the integral over gamma is 0 of f. And theorem 2.2 tells me that f has an antiderivative. Okay. Another way of rephrasing this is by saying that if we have a holomorphic function on an open set, there's no condition of convexity here, then every point in the set has a neighborhood on which f has an antiderivative. So we say that f has locally an antiderivative. Okay, so we can restate actually the corollary by saying a holomorphic function has locally an antiderivative. Okay, but not necessarily globally. Okay, why this is so? Because if you take a point z, take any ball of center z contained in omega, then this ball is convex. By corollary 2.2, f has an antiderivative on this ball, on this disk. Okay, and that's it. So this concludes this video. In the next video, we will finish section 2.1 by stating version 2 of this theorem of Goursat-Cauchy and another result about the differentiation of an integral depending on a parameter. Okay, so thank you for your attention.